Thank you very much, John, and thank you very much everybody who's logged in to listen to me talk today. I'm going to be talking to you about my PhD project of mapping part of the planet Mercury. Before I started my PhD, I was actually a exploration geologist for a mining company, so I was doing mapping on planet Earth before I started mapping the planet Mercury. For those of you who are geologists, then I hope to give you a flavour of some of the features and interesting processes that we get on going on Mercury. And for those of you who aren't familiar with geological mapping, I'll try and take you through the process of mapping itself. So we start off looking at a geological map, and this is the oldest geological map. It is the Turin Papyrus map. It's from Egypt, from 1150 BC, and it's a geological map with a purpose. Its purpose was to help find areas for greywacke, or a type of stone that could be used for making sculptures, and also to identify the location of gold mines. So it highlights the River Nile, and these areas of stone that were particularly good for making sculptures. And also it also highlighted the location of gold mines and that they occurred along an actual trend. And so whenever we make a geological map, we have to think about what it's going to be used for. And when it comes to planets, Don Wilhelms, who pioneered the mapping of the moon and some of the other planets in the solar system in the 70s, talked about it, the fact that the surface of planets are discrete rocks that through the sequences, through their positions, showed the shapes and processes that have affected the planet. And so you can see here in this image of Mercury that there are areas that are much smoother, with a few impact craters in, some very large impact craters that are connected and possibly filled in with some smoother material, and then rough bits in between. So you can see that there's a lot recorded on the surface of the planet, and a geological map can help us unpick the history of that planet, and also provide context. So whenever you want to study a particular feature on a planet, be it the inside of an impact crater, a volcano, or a glacier, or any of those features that you might get any rocky body in the solar system, geological maps help you focus in on features that you want to study and understand their wider setting. The process of mapping itself, because it's a systematic review of the surface of the planet, also gives you opportunities to pick up on features and processes that may not have been observed before during very busy missions when you're getting all sorts of data and planning the next day's activities. To give you a bit of an idea of Mercury itself, before we even managed to send any missions to the planet, we knew a few things. So we could tell its size. It's fairly small. It's about half as big as the moon and half as big as Mars, somewhere in between the two. So it's actually smaller than either Ganymede or Titan, so smaller than some moons, but it's actually much denser. It's the second densest body in the solar system after the Earth, but it's a lot smaller. We could also tell that it's got an interesting spin-orbit residence. A lot of people would say that Mercury's tidally locked, like the moon is to the Earth, but that's not quite true. Instead, for every orbit of the sun, the planet itself rotates 1.5 times. But that doesn't really tell us much about what's going on the actual planet, and that took really until the advent of the space age, because before then we could just see a pale pink dot in the Earth's atmosphere from the Earth, until the 70s when Mariner 10 was launched. It was the first mission to use flybys of other planets to get gravity assist to get to another body. It flew past Venus on the way there, and it was the first probe to visit Mercury, and it flew past the planet 3 times. Each time it flew past the same half of the planet, so we only ever got images of half the planet, but it still gave us our first insights into this rocky world that was basically dominated by impact craters. It looked very much like a lunar surface in many ways, with just impact craters over it. But there were some interesting features observed. So in this leftmost image, you'll see that there's this massive cliff here, and that was an indication that, you know, it's not just impact craters, there's possibly some tectonic activities going on. There were also large areas of smooth patches, which are seen in that middle image. And it was questioned whether or not those smooth patches were lava volcanic related, or if they were just large patches of impact melt, because it's still very early days. And then possibly most interestingly, from a planetary formation and understanding, it was the only other rocky planet in the solar system to have a magnetic field. So, or generate an active magnetic field. The Earth generates one and Mercury generates one. Neither Venus or Mars are actively generating a magnetic field, which for such a small body is quite interesting. But that's where most of the science was left. We couldn't see the whole planet, and we couldn't get enough resolution to really define many of these features. That was until 2004 when Messenger launched. That undertook multiple flybys of Mercury, but crucially managed to orbit the planet. And so it gave us the first global images of the planet, so we could see all parts of the planet, apart from those in shadow, permanently in shadow, and identified several new features, one of which is probably the most startling to come out of Messenger, are hollows. They're these features on the left here. They are a few kilometers across and no more than tens of meters deep. And they appear to be parts of the surface of the planet being vaporized by solar radiation, showing that parts of the planet are very volatile rich. This is something that's not seen really on any other planet in the solar system, unique to Mercury, and it's quite intriguing, really. They also identified the fact that there was explosive volcanism on Mercury. This orange spot in the middle of this central image here is called a facula, and it's thought to be the remnants of pyroclastic activities remaining on the surface of the planet. And finally, it confirmed what had been observed through radio astronomy, that there are, on both poles of the planet, there are craters that are permanently shadowed, and within them, there are areas of ice deposits, similar to those seen on the poles, permanently shadowed craters on the moon. Moving forward, the third mission, launched in 2018, is Bepi Colombo. And if I get some time at the end of the mission, at the end of this talk today, I'll explain a few bits about that mission. So I mentioned the magnetic field, and I also mentioned the density, and that helps us understand something about Mercury, which is quite interesting. Is that it's not really a rocky planet, it's more a ball of iron with a thin coating of silica and rocks on the outside. So you can see this comparison between Earth and Mercury. Mercury's mantle, silicate mantle, and Mercury's crust are very thin in comparison, no more than a couple of 100 kilometers compared to Earth's mantle, which is several thousand kilometers thick. And so it's much more large ball of metal, and that's what enables it to generate a magnetic field, even though it's so small. But that being the case, it's still very volatile rich. We saw those hollow features that I mentioned on the surface. So it's not only does it have a large iron core, it's also got a volatile rich outside. And this can actually be seen from Earth using places like the McDonald Observatory, where they look at sodium, and you can see that Mercury actually generates a tail of sodium in the solar wind. Sodium is being blasted off the planet and extending away from the surface to up to 2.5 million kilometers, which at times, when you don't have any cometary activity or other things like that, makes it some of the largest objects in the solar system, if you exclude things like Jupiter's magnetosphere and the solar magnetosphere, for example. Just to give you an idea of scale on that, the little red circle on the image on the left here, that is where the moon would be orbiting if the Earth was in the middle of the image. So you can see these are huge features coming off it, and that's linked to Mercury's volatile surface. But being a geologist, I want to look at the surface of the planet, and we get these pictures like this, and it looks quite grey and boring in some ways. In fact, Mercury has a lower albedo contrast than the moon does. So where in the moon you've got those quite bright highlands and lowlands of those lunar mares, those dark lava patches that make up the face. Mercury doesn't really have it. It's much more uniform in some ways. Thankfully, the missions that go there have much better eyesight than we do. It's got multiple bands and we can enhance them. And so you get much brighter pictures than this, and you can see using enhanced colors, there's a lot more going on the surface of the planet. There are bright patches inside large impact craters. There are large areas on the north pole of the planet that are quite light, bright features. There are other parts of the planet that are much darker features. And so you can see there's a lot more going on, but then you need something like a map to really understand it and contextualize it. And this isn't anything new. Mariner 10 produced 1 to 5 million scale maps. So that's every millimeter on the map would be about 5 kilometers. But they only produced it for about half the planet. The reason being that they could only half the planet was ever seen. And in fact, it's less than that because the resolution was so poor. So there were gaps missing for parts of it. But it still gave you an idea that there are lots of craters, and then there are various units in between them of different types. I won't go into them for these particular maps, but I'll talk about them a bit more in my map. And my map is part of a project across Europe to map all of Mercury using the messenger data at a scale of 1 to 3 million. So Mercury is divided into 15 quadrangles. And so far, we've already got 4 that are published. That's these 4 up here. Then all these others that are in red are underway at the moment. There are currently 4 at the Open University. This one up here by Jack Wright has already been published. And then 2 of my colleagues at the moment are working on these other 2 in green. And I am currently mapping this area here in blue. In fact, they will have an additional one starting in February at the Open University. Will start mapping the South Pole here. So, but if we look at my quadrangle in particular, I'll take you through how I map. So you start off with your base map, which is what we're going to start to map with. We use messenger products that come at 166 meters per pixel, which means that you could easily hide several houses in there. You might just be able to see something like a supermarket as 1 pixel. So they're still pretty coarse, but we are covering areas similar in size to that of Australia. But the thing with Mercury is that it's got no atmosphere. And so you can't actually just use you can't use this 1 single base map. You actually have to use multiple because of illumination. At different times of day, the sun is at different parts of the sky. So in the morning, the sun rises in the east, and you get inside craters, you get shadows forming on the eastern wall, so you can't see what's going on in there. In the sunset, towards the end of the day, you have the sun is in the west, and the shadows are hiding the western portion of the inside of craters. And then you have midday. Now, midday gives you a view of all the crater, but because the sun is overhead, there's no diffusion, there are no shadows, and so all you get is really a strong reflectance. And so actually we use multiple base maps. Just to give you an idea, this is part of my mapping area in 3 different illuminations. And you can see here in the west illumination, this part of the crater, the floor is very clear, but the location of this large crater rim is not so clear. Whereas from the east on this side, you can see the crater, the edge of the crater much clearer. Likewise, this cliff along here is much more defined in this illumination, whereas this side, it's all in the sun, and so it's oversaturated. So we basically need to use both to make sure that we can see the inside of craters and identify all of them. Finally, we use local noon, and you can see what I mean about the lack of shadows. This area here is a crater in here and here, but you can hardly identify it. Similarly, the crater here is almost gone. But it is useful to pick out albedo features. So you can see that these features here, these rays that are coming through a crater outside to the north of these image, are clearly seen covering the surface, but they aren't seen on any of the other 2. So you have to use multiple data sources to really understand what's going on. Luckily, computer technology means that within a geographical information system, you can have multiple images loaded up and just turn them on and off to flick between the two, or two or three, to work out what's going on there. Now, we're mapping at a scale to 1 to 3 million, so that means that any feature above 3 kilometers is mappable at basically becomes a 1 millimeter feature on the surface. That's on an A0 sheet. That will not be on your screen because I've had to shrink everything down and simplify it a bit, because otherwise it would be too big to see. But as I've talked about, the number one thing that really mentioned over and over again on the surface of Mercury is craters. And so that's what I did for the first 6 months of my PhD, was drawing circles. Now, we didn't quite go down to 3 kilometers with them. We went to 5 kilometers. This was basically following everybody in the same mapping units to make sure that it would follow between maps and they all join up. And 5 kilometers was chosen because you're already into the realm of secondaries on Mercury. Secondary craters, which are generated by other impact events, are up to 8 kilometers in size. And if you go any smaller than 5 kilometers, you're going to be saturating in the map with lots of smaller craters without providing any more scientific detail. And in fact, when you get to above 20 kilometers, not only do you start to get the rims, but we start to be able to say, map out the ejecta, and crater floors become large enough to also be mappable. Once we've done that, though, we've outlined all those features. We need to start looking at other features on the planet. And this is where we start to talk a bit more about the geological endogenic processes going on within Mercury. Because what you might see is if we start, there are some linear features here that are in shadow. There's some other ones here. Now, these are example of those cliffs, or rupees, as they're known. This is one in another part of Mercury. It's very clear that you can see there's a cliff going diagonally across the screen, marked by that dotted line, and then you see it's cutting across craters. So you see these craters here are no longer fully circular. Even this big crater here is partially cut by it. And if we look in a kind of orthogonal view at that with some shading that shows the topography, so the left of the image there, that red is much higher up than those areas to the right of the image in blue. You can see the cliff. It's a bit exaggerated, the topography there, but you can see the cliff, and you can see that it's really cut these craters so they're no longer circular. And the reason for that is these cliffs, these rupees, are generated by tectonic faults. You have one area of the crust rising up and being thrust over other parts of the Mercury's crust, and as it does that, the craters that were right in the middle of it, they stop being circular as the one part gets squeezed above the other. Now, these are the most common structural features on Mercury, and they're all compressional. You do get some extensional features, but they're all inside large impact basins, and the reason that Mercury is dominated by these compressional structures is because of its small size. It's small, it's got a large surface area, and so things that do that, they cool and they shrink. And so Mercury has, it's estimated to, its radius has decreased by 7 kilometers since it formed. And if you've got the rocky outer crust, the hard part on the surface, it's got to accommodate that shrinking. And it can't do that by any other way other than cracking and generating faults. And so the surface of Mercury is covered in these lobate scarps, these cliffs, generated by shrinking and cooling. And in fact, this is a process that we think we're fairly sure is still going on. Here's a Nature Geoscience paper by Waters in 2016 that showed that there are these very small scale features, small for Mercury anyway, and these features would not last very long. They're not very deep, they're not very large, and space weathering on Mercury would quickly erode them away and obscure them, and we wouldn't see them anymore. And so it's thought that actually Mercury is still a tectonically active planet. So back to my map. As I say, we start to draw on the lines. and you start to see some features. So these are the faults all in red here. You see you've got those nice ones there. But it's not really telling us much of a story. You might be able to pick out timing. You might see that, oh, it cuts across these impact craters, therefore it postdates them, it occurred afterwards. But you then want to know, well, what's going on in the rest of it? And that's where we start to look at the areas in between. So I'm stopped drawing so many lines and getting ready to color in. And so we look at the surface itself to try and divide it up. And Mercury's surface has, since 2010, been divided into planes. These are units that are based on their morphology or their texture, how they appear. And so you've got some areas that are quite rough, bumpy, and other areas that are much smoother. And so we can use those to work out and divide up the surface of the planet to try and work out the history that's gone on there. And so within my map, and for many others, it's been divided into 3 main plane units. You have the smooth planes. These are fairly flat, and they have relatively few impact craters, and so we can suggest that they are the youngest. And then you have an intermediate stage and then an intercrater planes. These are not only have more cratering in them, but they are also more hummocky and more rolling, so they're less flat and smooth. The intermediate planes that I just glossed over for a second, they're actually a bit controversial. It has been suggested by people like Jennifer Witten that they are areas of either smooth planes that have been modified by nearby impact craters, or they're intercrater planes that have just been lucky enough not to get so much modification. However, for me, there are areas of intermediate planes that I can see that are away from nearby impact craters, and so I would suggest they are a separate discrete unit to either the intercrater or smooth planes. You'll notice that there is a color difference to them. And for those of you who work on things like asteroids, you might think, well, the reddish end member should be the more space weathered than the bluish red end member because of space weathering. However, there is a compositional difference that tends to account for, we think accounts for this. The smooth planes tend to be lower in things like magnesium and iron and higher in silicon than the intercrater. The intercrater planes also have quite a high level of carbon and sulfur in there. In fact, for all of Mercury, I'm fairly sure sulfur is in similar level weight percentage to iron in some of the rocks. So it's a very volatile, rich planet and slightly compositional interesting. Now, the question is then, where do these come from? Now, if you're familiar with the lunar highlands, you might go, oh, is that similar to the intercrater planes? But lunar highlands are completely saturated with craters. So you've got one crater and there's no space for new craters. Any new crater just smashes into a part of an older crater. Whereas the intercrater planes on Mercury aren't fully saturated. So they're not at the original crust of the planet cooled down. So they must be younger, and so they must have formed through some other process. And luckily, we can look at the smooth plains to the north of the planet and pick out features that give us some ideas. Or you can just read the title of this slide, it also gives it away. But you can see that there are these estuaries that have been picked out by Paul Byrne. And while it's not caused by water, what you have is deltas and things like that that are generated, and islands as lavas have flown through and around rocks and eroded them away and then deposited them out there in places like these basins. So we think that pretty much all the surface of Mercury is various different ages and different compositions of lava flows. It should just be stated that there's still some problems matching up some of the compositional data with the morphology data on Mercury. That's still something that we need to work on going forward. But we can still see these are significant events. So this is, again, the North Pole of Mercury is up here, and you've got this area of smooth plains, those light yellow areas. And while it's probably not one single event, it's still a very closely timed with when these occurred. And so this is a quite huge area of lava flows that formed in a relatively short period of time. And it goes quite far south. So if this was Earth, it goes as far down as 50 degrees north, which is about where Cornwall is. So if you can imagine lava flows going all the way from the North Pole to Cornwall, it's a huge area to be covered. And in fact, we estimate that it's somewhere between 10 to the 6 and 10 to the 7 kilometers cubed, which is, again, a huge number, hard to visualize. But we have had eruptions like that on Earth. And similar size is that forming the Siberian traps, which is associated with the Permian-Triassic extinction, which wiped out 96% of marine life on Earth. So these volcanic events, wherever they happen, are significant features. So this is the map with those faults, and as I say, we start to fill it in with those those different plains units and also some crater units. So those pink are those lighter yellow ones, and the brown are those intercrater plains. And you can see there's some more salmon colored ones here, which are those intermediate plains. There's also some units here that have fitted in with Rembrandt itself. So you can see we start to work out a history of the surface of the planet based on the levels of the textures and the morphology of it. You'll also notice that I have classified the craters. That's using a 3-class system that's based on their morphology again, and it's linked to how much they've degraded, so how much they've been exposed to space weathering and processes like small impact, space gardening, stuff like that, that can degrade features. So you start off with the least degraded craters. These have lots of terracing on their walls, and the boundary between the floor of the crater and the wall is quite sudden and quite sharp. And you can see that the ejecta goes quite a way around, or at least if you get your eyes into looking at the ejecta of Mercury, it goes quite far around it, and it's quite clear and distinctive. You can pick it out. As these craters are exposed for a longer amount of time, they start to lose those terraces. These crisp lines that we see on the walls have kind of gone, they've slumped down. The ejecta gets closer in, less clearly defined, and you get more superimposing impacts on top. Until finally you get to the most degraded craters here, where there's a lot of overlapping impact craters, and the boundary between the wall and floor is blurred, and it's very hard to make out much ejecta. Now, the Mariner 10 used 5 classes to break up Mercurys, and that was linked to 5 lunar classes and was tried to give an age range. However, because the rates of space weathering are size dependent, I'm not going to do that here to give a specific age range, because smaller craters might lose those features much faster than bigger craters. So so while I'm not going to give specific ages, you can start to pick out relative things. And so we can use relative comparisons of different units on the planet to work out different features. So whether it's overlapping craters, and you can see here that you've got a large ejecta from this young crater overlapping this intermediate age one, which has got a smaller ejecta because it's been lost to some forms to space weathering. Similarly, you can start to see things like relative timing. So you've got this basin over here. This is the Rembrandt impact basin. And within that, you've got smooth plains filling it in. So you can tell that the smooth plains in this area are older than Rembrandt, but Rembrandt is at least older than some parts of the intercrater plains. Rembrandt is a big impact basin. It's 750 kilometers across, which if was to happen to Milton Keynes, would cover a significant part of, well, basically all of England and Wales, and get you as far as the Scottish border or a trip to Brussels. Within Rembrandt, there are also these tectonic features that I've highlighted before, but there are also some extensional ones, but I don't have enough time to really talk to you about that today. And then finally, you can see that we can put on the topography, and you can see the Rembrandt impact basin here. And instead, you can see that there's another impact basin over here. And if we look at those features, we can see actually that this area here well, we don't have the clear ejecta around it, so it's an older basin than Rembrandt. There is still smooth plains following it. So you can say that actually smooth plains like to use low-lying depressions or possibly older impact basins. So you can start to build up a geological history. And you can also see here, these yellow diamonds are volcanic vents, and they are those pyroclastic features I mentioned earlier on that were identified by Messenger. And you can see they form inside the youngest impact basin, impact craters. So while smooth plains may be covered by and superimposed by impact cratering, showing that they've stopped, it's possible that these pyroclastic features occurred much more recently because they post-date those features. So you can use that to build an approximate geological history. And you can see here, this is very rough because I haven't done much crater counting or anything like that with my maps or anything at the moment, but you get an idea that the intercrater planes are older than the smooth planes. We got that from both texture and the superposition. And then you can get timing of when the older basins were, Rembrandt, and some of the volcanoes and the tectonic activity. So you can start to build up a story of how the planet evolved by looking at those relationships. Now, if I mentioned before that we like to use geological history and provide context for other studies, so you can do that through looking at the map, but you can also identify new features. And that's where I went to next with my project. I was looking at these volcanic vents and I wanted to understand them more. Now, we saw that they had a facula, this red orange spot around them, but you can also see that they've got a pit inside them. And what we interpret this pit to be is an explosive hole dug out by the eruption. So you have both the facula, which is caused by the pyroclastics, coming out in a kind of umbrella shape. You can imagine that from, well, you can see that on Io going on at the moment in another airless body. You have the ash depositing, and that gives you that bright halo. Now, if you look inside some of these vents, as Professor Dave Rothery did in 2014, you can see the interior of these vents sometimes has structure. And if you look at these structures, you can kind of work out some possible relative timing. And that's interesting because that shows that these structures were erupted more than once, with this area here where it's roughest being the most recent, and probably mantling those areas around it. Now, I decided to take this one step further. I knew I had some in my mapping area, but I decided to look at all the ones on the planet to get a better idea of how often explosive volcanoes erupted on Mercury more than once. And so I started looking at these features and I looked for signs of being compound, and that could be a superposing feature. So you have multiple vents in this image on the left, with the one in the middle being the most recent. Or in this right image, you can see that actually there's a sequence of eruptions where you have one big vent and then multiple smaller vents going on. This is in contrast to those that are not compound vents. So inside this crater, you've got this single hole here with no internal structure. So it could well be that that erupted just one time. I mean, it could have erupted multiple times, but we've got no indication of that. Or similarly here, where you've got this large vent here, but with no internal structure other than a slump towards the north. And so I did this review and looked globally, and basically found that of all the vents that I could identify, about 70% had erupted more than once, with the remainder appearing to only erupt once, or only having signs that it erupted once. This is important because it shows that these vent sites are active. Now, as I mentioned before, Mercury is a shrinking, contracting world. It's quite hard to get material to rise up from depths during a compressional system, and you need a way of recharging it for the volatility to continue to have multiple explosive eruptions, either from assimilation of material in the crust or by recharge of volatile rich magmas from deeper down in the crust. This is interesting for those of you interested in more things like the formation of the solar system, because you need to have a way of making a volatile rich planet, and by better understanding things like this, we'll have better grasps on how the volatile budget of Mercury. You need to make a volatile rich silicate crust, but also a very large iron core. And I think people in the Mercury community are currently favoring some form of nebular differentiation to cause that, because large impact events seem to amalgamate afterwards. But that really needs to be considered as part of a larger solar system evolution. So that is my map, and that's some of the ideas that have brought into it. And they've identified some features that I can understand and look at. Unfortunately, many of these pyroclastic vent sites here, these facula, were too low a resolution to include in my study. And that's where Bepi Colombo comes into, because Bepi Colombo, I hope, will give us much more better resolution images for many of those features, especially in my area of the Southern Hemisphere, that can't be studied as detailed as I'd like. And even though I've identified them with my map, I can't do the detailed studies that I'd like to follow on with. It's launched in 2018, but won't get into Mercury until 2025. And in fact, it won't get much science data back until 2026. Here it is at the moment. It's halfway between Earth and Venus. It flew past Earth on April this year, and is on its way for this first of 2 flybys of Venus. And after that, it will undertake 6 flybys of Mercury before it finally gets into orbit. The reason for that is that Mercury is incredibly difficult to get into. You have to be constantly into orbit around. You have to be constantly slowing down to make sure that you don't just whiz past it. So you have to get in and be caught by its gravity. And so, in fact, it takes more change in velocity to get into orbit around Mercury than it does to fly by Pluto. So this is Bepi itself. And the interesting thing about this mission is it's 2 satellites in one. In fact, 3 satellites, if you include the transfer module that's using ion thrusters to get there. When it gets to Mercury itself, it will then split off, and the transfer module carries on around the orbit of the Sun, and then Bepi Colombo will go into orbit around Mercury. The Japanese satellite, MIO, will split off first, and then the thermal selection collar will also then split off before Bepi itself goes into orbit, into a lower orbit around Mercury. And you can see here it's got 2 different orbits for the 2 different modules, and the reason for that is that they have 2 different purposes. MIO is really looking at the Mercury environment and the interaction with the Sun and the solar wind, and so it's able to go much further out into the tail around Mercury and look at things like the solar wind and the magnetosphere and sample more of that, whereas Bepi is designed to really study the surface of the planet itself, and it's in a much closer, smaller orbit. And so it will spend a lot more time close to the surface of the planet, certainly, and will provide us much better imaging of the southern hemisphere. You can see Messenger's orbit to the right was very elliptical, and so the southern hemisphere of Mercury has a much poorer data used to study, and so Bepi will really give us some of the best images and data for the southern hemisphere. On board the 2 satellites, as I say, MIO is magnetometers and plasma science mostly. Bepi has a great range of instruments for studying the surface of the planet. It's got various different thermal imaging, both infrared, UV, and also X-ray data will be collected. It also has a laser altimeter, which will be excellent for studying things like the faults and some of those volcanic vents. And it will also, most excitingly, I think for me, is symbiosis, which is the camera on board. It will include stereo image. It's got stereo image capability, as well as the ability to image about 10% of the planet will be imaged at 5 meters per pixel, with the rest of the planet imaged in color up to 100, with a color mosaic map for 100 meters, and there'll be various black and white images at resolutions in between. So it will give us much better than the current 160 meter average maps that we've got for Mercury, and in fact for color maps they're 250 meters. So it will give us much more information to help us follow up on the planet Mercury. And so I'm really looking forward to when symbiosis gets there and gives us the ability to look at some of those features that have been identified. So in conclusion, mapping helps us understand a planet and its history. by providing some context, and you'll be able to work out how different parts of the planet relate to each other. It also provides a great way, because you're systematically studying the planet, to identify features that need further study. And it provides a great way of getting ready for Bepi Colombo by providing areas that what we do know and leaving areas where we've still got further questions. And so with that, I will finish there and take any questions.